So in this video we're going to continue finding antiderivatives by the process of integration. We're just going to add a few more little details as we go through these problems. So I'm going to do 4 problems, 4 examples from the section 4.1 in our book. So if you want to get your books out and look at the problems that I'm doing and at least kind of observe what the directions are saying, that might provide some insight to these problems. All right, we're going to start on page 256 with example 49. This is the given differential equation. It's a given derivative. We're asked to find the particular solution to this differential equation. And all that means is let's just go backwards and find what y is equal to. We're going to find what y is equal to, but we're going to use this ordered pair right here. This is an ordered pair that doesn't fall on this differential, but it falls on the regular graph y. We're going to use this ordered pair to find the particular solution. What you might notice is that this is different than what we've been doing, and this just says y prime is equal to this linear function. And if you think about it, if this linear function is our derivative, then the antiderivative, the y equation, is going to be quadratic. So at least we know what we're looking for. Alright, so for this particular problem, what you might want to do to find y is to do what we call separate the variables. This is one strategy for finding y equals. Let's separate the variables. And that just means that you can kind of notice that we have an x over here on the left hand side of the equation, we have an x over here on the right hand side of the equation. We want to put all our x's on the right hand side of the equation. So even though this notation represents just one thing, a rate of change, what we do is we actually go through and we separate by saying, well, let's pull over the dx to the other side of the equation. And if you think about what we're doing here, okay, we're kind of saying we're dividing by dx. So if I'm dividing by dx, then I can multiply both sides of this equation by dx. So by multiplying the left side of the equation by dx, I'm somewhat canceling the dx's, the differentials, okay, over here, but I'm going to go ahead and multiply, so to speak, this linear equation by dx. So separate the variables. It's our first step. What we're looking for is a differential on both sides of the equation so that I can integrate. So right now I have a differential on the left hand side of the equation. It's a differential in y, and I have a differential in x on the right hand side of the equation. Okay, now that that's accomplished, separating the variables, I'm going to bring in the integral symbol. And if I bring in an integral symbol, what I do to one side of the equation I have to do to the other. So just kind of stop and pause and think about what I've done from this step to this step. I've just brought in the integral symbol. Okay, and as I pause and I look at this, in order for me to integrate, the symbols that are necessary are two symbols, an integral symbol and a differential. Integral symbol, differential. All right, well, let's work on this side of the equation. Okay, if I say, well, let's integrate the differential in y, I'm really saying there's a coefficient here, or an integrand, if you will, of 1. Well, what's 1 the derivative of? Well, we've done a little practice with that. 1 is actually the derivative of, you might be tempted to say x, but this is the variable of integration, so 1 is going to be, in this case, the derivative of y. And if you wanted to, you could put plus c over here, but I'm also going to have a plus c over here when I integrate this side of the equation. So if I have a c here and a c here, really, if I collect them, I just have a c. And we're just going to put the 1c value, the constant integration, on the right-hand side of the equation. So integrate the left-hand side of the equation, I get y equals, and notice this is great. I'm trying to look for y equals. Okay, coming over here, let's integrate this integrand. So I'm looking at this linear equation here. It looks like it's ready for integration by using the reverse power rule. So working with this first term here, I'm going to keep the 1/2, I'm going to keep the x, okay, and I'm going to take the 1 power and I'm going to increase it to 2, and I'm going to divide by 2. But before I divide by 2, I'm thinking I'm going to have a complex fraction, so instead of division by 2, let's just multiply by a half. So I'm just going to put the multiplication by a half in front here. That's the same thing as dividing by 2. Moving on to this term right here, well, what is 1 the derivative of? Well, it's the derivative of x. And again, if you wanted to write in x to the 0 and perform the reverse power rule, that's totally acceptable too. But you might just notice that 1 is the derivative of x. Okay, well, here's where we're going to include our constant of integration. So what we have right here is what we call the general solution. This is general. It's not specific, it's just general. It's a family of functions that could be an antiderivative to this differential equation. Okay, and we could stop here. However, what we were given was a point that satisfies the y equation. Well, if this point satisfies the y equation, remember this is x and this is y, we're going to substitute these values into the general solution so that we can find the c value to get the particular solution. So where y is, replace it with 2. Clean this up. Let's make it 1/4. X is 4 from the given initial condition is what it's sometimes called. We're going to square that. So 1/4 x squared minus 4 plus c. Let's perform the calculations to find the value of c. 16 divided by 4 is 4. 4 minus this current 4 plus c. These will cancel. So my constant of integration is 2. So that's the specific constant value right here. So now what I'm going to do is I'm going to come back up here and I'm going to replace this c with 2 and I will have found the particular solution. So rewriting the general solution, 1/4 x squared minus 4 plus 2. Again, that's called the particular solution. I know exactly what c is because I had a point that was on the regular graph, if you will. Alright, now to save some space, what I'm going to do is I'm going to come over here to the right-hand side and I'm going to do another problem. Okay, and the next problem I'm going to do is problem 52. Same objective. We're going to find a particular solution for this differential equation given an initial condition. This ordered pair satisfies y, not y prime, y, so we're going to use it when we get to the general solution. All right, let's go backwards and find y by integration. So we see we have to separate some variables. We want to keep our y's on the left-hand side and the x's on the right. So multiplying both sides of the equation by dx, we end up with this equation. I have a differential on both sides of the equation, so I'm going to bring in the integral symbol. Now we're ready to proceed with the notation. It's requiring us to integrate. Like the previous example, 1 is the derivative of y. And again, you could put 1 y to the 0, perform the reverse power rule. You're just going to get y. It will have a plus c, but we'll save that for this side over here. So y equals, okay, looking at this integrand right here and looking at the first term, I'm going to perform the reverse power rule, increase 2 to 3 and divide by 3. So we have 1/3 x cubed minus, antiderivative is x, include the constant of integration, and remember this is the general solution. If I didn't know what initial condition I had, if I didn't know a point on the original graph, I would be done here. There's nothing more I could do. Alright, based on the variables in the equation, I know this is x, this is y. So I'm going to replace y with 3 and x with -1. Complete the computations to get the value for c and have a particular solution. All right, in my work to get c by itself, to solve for c, I think I'm going to go ahead and just subtract 1 from 3. That might make it easier than try and work with, collecting these together. So if I subtract 1 from 3, I'm going to have 2 equals negative 1/3 plus c. That makes it easy enough to add a third over here to 2. So I guess I'm going to end up with 2 1/3 equals c. I will convert that to an improper fraction, though. We don't typically work with mixed numbers. It's not wrong, but common practice just has us usually rewrite that as an improper fraction. All right, let's go back up and find the general solution so that I can rewrite it with the constant of integration. So this is what we call our particular solution. And as a real quick note, let me just say this. You could check your work by differentiating. If I were to find the derivative of this cubic equation, if I were to find the derivative, I should end up getting back to what I started with, this differential equation, that derivative. Okay, noticing the time that we're at, I think I'm going to go ahead and just stop right here, and you can just start the next video. I think I'm going to need a little more than 4 or 5 minutes for the last 2 examples. So just go ahead and start the next video at this point.